This mini lesson on simple machines is going to focus on the inclined plane. The inclined plane is probably one of the simplest of the simple machines to create. All an inclined plane is a flat surface set at an angular incline with no moving parts. So we could have a little ramp for a bike, something to help us load a heavy object in the back of the trailer, or it could even be a mountain pass with all of its little zigzags. The inclined plane gives us the ability to lift objects by either pushing or pulling the load. Either way, we're doing the same amount of work, but with a lot less force. Remember from one of the first videos you watched that work is defined as the amount of force required and the distance to move that force. Both of these objects are being brought to the exact same height. The one going up the inclined plane, though, has a greater distance, so it's going to require a lot less effort force to do that. The box we're lifting straight up has a lot lower distance to go, so the force is going to be higher. With every simple machine, there's a force-distance trade-off. In each of these pictures, you can see that we're going to take this rock or boulder, move it up 1 foot of vertical height. The longer you can make the ramp, however, the less effort force it's going to require. That's what we mean by that force-distance trade-off with simple machines. For the inclined plane, our ideal mechanical advantage is still found by taking the distance of the effort divided by the distance of the load. What's different is where we take those measurements from. The distance traveled by the effort is going to correspond to the length of that inclined plane. The distance traveled by the resistance is going to be the height that we raise it up to. Okay, so either way, the goal is to get this cart up to this position. So I could have either chose to lift it straight up, or I can choose to roll it up the incline. Based on this scenario, my ideal mechanical advantage is going to be the length divided by the height. So to find the ideal mechanical advantage of the inclined plane above, I'm going to take 15 feet divided by 4 feet and get a mechanical advantage of 3.8. I can also figure out how much effort force would be needed to push the cart up the hill. Recall that the ideal mechanical advantage can also be set equal to the ratio of the force of the load over the force of the effort. Use your ideal mechanical advantage, use the known value of the load you're trying to lift, and when you solve for the force of the effort, this is in theory how much effort you should have to put in based on this inclined plane that we built. Our actual mechanical advantage, however, is what we get when we actually try to do our simple machine. So again, it takes into consideration things like friction or other losses of energy, just part of the system. So the actual mechanical advantage of this inclined plane above, we would need to know how much effort force was put in. The load hasn't changed, that's still equivalent to 50 pounds, but now my effort, what I needed to put into the system, was 20 pounds. My actual mechanical advantage is 2.5. This gives us an efficiency rating. My actual mechanical advantage divided by my ideal mechanical advantage, multiplied by 100 gives you a 67% efficiency rating. If you have any questions about finding the ideal mechanical advantage or the actual mechanical advantage of an inclined plane, please make sure you ask those questions in class.